whiteboard. Now come on over here. Hello, hello, Zoomers, Roomers, everyone, everybody. So here's your mouse. Just only they can see this and only they can see this. So anything you want to show them has to be over here.
Yep.
Okay? Hi.
Thank you.
Go for it.
So I wanted to start off by asking what you all responded, and you all had really good responses to the question, so I feel like it's going to be an easy discussion. But I wanted to start off by asking what a categorical variable is. Anyone has any answers, what they put? Mm-hmm.
So I use this acronym that's C, B, and O for categorical.
Sorry.
Go ahead. I'll let
Categorical variable. That's binary, nominal, and ordinal. So that's how I remember categorical variable.
Mm-hmm.
Where we have labels and we have the categories.
Yeah, that's great. Yeah, and I like the acronym too.
C, B, and O. Yeah.
Can you repeat it for the recording?
CB.
Yeah.
CB
And O.
and O.
Yeah.
Yes. Okay, because it was for categorical.
Categorical, binary,
Binary.
nominal, and ordinal.
Nominal and ordinal. Yes.
Variable. Yeah, that's
Yeah.
how I remember.
That's a really helpful acronym, I think. Yeah. And you got to my next question before, because I was just asking like in terms of labels, but yeah, those are the subtypes of the categorical variables, so great. And then going into the quantitative variables, what would you describe as a quantitative variable?
It's a number that actually measures something, and it can be discrete or continuous.
Yes, exactly. Does anyone have any examples of other types of quantitative variables? There were a couple more.
Height, weight.
What?
Like human beings' height.
Height and weight, yeah. So like interval and
Ratio.
Ratio, yeah. Yep. Any others?
Temperatures.
Temperatures, yeah. Any of the like labels that we called them? So we got the ratio, interval.
Percentages too?
Oh, which
Can
one?
you have percentages? Yes.
Percentage.
Yeah. I was thinking like.
Well, examples are good. Percentages, yeah. The numbers are numbers. That's the thing,
Yeah.
right? There's one of them, there is a max. One of them, there's no maximum.
Yep.
And then one of them has at least a minimum of 0, right? Yep. You want to phone a friend? We're telling you, test score, for example, max 100%. What type is that? I can't find my notes. Starts with B. Hey, yep. See who's there. Yeah.
And then does anyone remember the other type of variable that has a boundary? Yes. Yeah. So it's interval, binomial, count, ratio, and then there's some couple other ones, or one or two that are kind of questionable. The kind of handshaking is kind of trying to insinuate.
Continuous?
Yes, and then the counterpart to that.
Discrete.
Continue-ish.
Yes, continue-ish. And can someone describe what continuous or continue-ish means?
Continue-ish is when there's like, okay, a scale 1 through 6 for your pain or something, but you operationalized it by being like, oh, okay, well, it's a 1, it's 2, it's a 3, and that becomes more like when you do averages and stuff, it can be between decimals.
Mm-hmm. So to repeat for the Zoom, trying to remember that, when you have like a scale of items, so like maybe 1 to 5, 1 to 6, but you have enough data points that you're kind of saying like this is continue-ish because it's about continuous, you're like guesstimating. Treating it that way, yeah.
Even though it's true or not.
Yeah. And then the last one, continuous. Anyone have a definition for that one? Or an example?
I'm pretty sure it could be a continuous.
what was it?
Temperature.
Continuous is harder because it's harder to find in
Yeah, I
Yeah.
couldn't think of an example. That's a good one.
It is.
but yeah.
Weight, time.
Population. Like little population. Or is that?
That's more continue-ish, I would think.
Yeah, if we have another pandemic, we could get back to zero. Not to put a damper on it.
But like with temperature, like having, being able to go negative and like positive, not necessarily that negative is needed, but that there's a more range that you can have possibilities. And so those are all great responses for the first one. So going into the second question, now that you know what quantitative variables are, if we're going to look at them in a distribution, what are some of the features that we're going to pay attention to when we're looking at the distribution?
Tendency, dispersion, skewness as well.
Yep, exactly. Yeah, so variance would be an example of which one? Yes. Any other examples of dispersion?
Standard
Standard.
Yep. There's also one more that could be,
IQR.
yes, interquartile, yes. And then going back to the central tendencies, are any examples for those?
Mean, median, mode.
Yeah, the easy ones, the sixth grade.
True,
It's the same thing in sixth grade.
Yep. And then the last one, skewness. Any examples of those? Think of recent images shown on the screen. Yes, exactly. Oh, sorry.
That's okay.
I mean, I'm done.
Nope, you're new.
That's the end of number 2?
Yeah.
Synonyms for skewness?
Asymmetry.
S1?
Yep.
I can think of one more that I use. What are those? Synonyms for
Oh, it's,
was asymmetry. Lopsided.
yes.
That's another informal term. Yeah, good job. What's our first time?
All right.
You got one to do.
I have
Unless you wanna
one.
talk about your theme song.
I'm happy to talk about my theme
Okay,
song,
so you do
so
both?
I'll do both. Yeah.
So,
So the difference between standard deviation and variance, I think it's best to start with how do they relate to each other. Anybody have an answer for that? How they're similar? Yes, they're both measures of dispersion. They measure it in very similar ways. Anyone kind of the salient feature of how they're different between variance and standard deviation?
One's the average distance, and one's the average square distance.
Yes. Which one is the average squared difference?
Standard deviation.
Variance.
yeah,
Variance.
Variance.
Average squared is going to be the variance, right? And then when you square root that, then you get the standard deviation. One of the things I noticed, that was one of the things I noticed in the responses, some people were switching up those terms. You had the definition spot on. You just were referring to standard deviation when it should have been variance and vice versa. So the variance is the average squared distribution about the mean, and the average distribution about the mean is going to be the standard deviation when you square root that. One thing that some people did add into their responses of what's the difference between the two that I thought was really, really good was the standard deviation is putting it back into the units of the variable that we're talking about. So if we have a sample of 50 high school students and we have an average of 15 years old for those students, and we have plus or minus, or we have the variance is 25, that's not in the units of years. We can't say, the variance is 25 years. Once we take the square root of that, then we can say the average age of the students in our population is 15 years old plus or minus 5 years. That would be the standard deviation. You're saying the exact same thing. If you say the average age is 15 years old with a variance of 25 or a standard deviation of 5, it means the same thing. It's the measure of dispersion. That's how they relate to one another. But the standard deviation can be really important and really useful because you're putting it back into the units of the variable that we're talking about. Which one necessarily comes first?
Variance.
The variance. The way I like to think about this is variance is one word, it comes first. Standard deviation is second, it has two words. You can also think about, you can get either one, right? most of the time in a paper, you're going to get the standard deviation. You simply square it, you're going to get the variance. If you have the variance, you square root it, you're going to get the standard deviation. But that's how I like to think about it. Variance is one word, so it typically comes first. Standard deviation is two words. It typically comes second. Any questions?
Why does it have to be that way?
Why does it have to be that? My understanding of it is because we cannot simply take the square root of something if we don't have it yet. So with the variance, if we have a sample of 50 students, right, we're going to take the difference between one observation and the mean, and then we're going to do that for the second observation and square it, and do it for the second observation, the third, all the way up to 50, and we're going to sum all of those together, and then we're going to divide it by n, right? We're going to divide it by the 50. That's how we would get the 25 variance for the students who are in high school. But we can't square root that just yet until we have that 25. So that's why the variance necessarily comes first, and then we square root that to get back into our units. Any questions?
Otherwise, the positives and negatives cancel, and we get all this stuff.
That too. Yes. Yes. Anybody want to share their favorite song? Or their theme song? Anybody from Zoom?
I built the playlist this morning. Go for it.
I was the happy person.
The happy person.
Mhm.
Okay.
I had to choose a Queen song, obviously, but no, I chose "Don't Stop Me Now" because I feel like it's like really upbeat, and once you hear that song, you're just like,
Yes.
yeah, okay, like your brain's reset, you're just like a toddler, like.
Exactly.
You know, yeah.
Plus, you're enrolled in this class, so there's no stopping.
Yeah.
We've got the train
I hope
rolling.
so.
Yes. Yes. For anyone interested, you may not be. I have had the same theme song for all 4 classes I think I've taken with
That's
Lisa
what I
now.
feel.
Yep. It has always been, oh my God, the Bee Gees. Yeah, Staying Alive. Yeah, that has been my theme for every time I've been in this class, including as a TA. So I will be staying alive with all of you this semester. Any other questions about the third question or anything? Yeah.
So you calculate standard deviation, so you have to, is standard deviation itself squared? I don't know what I'm asking, so like technically the standard deviation is squared, so then technically the variance, wouldn't that be like?
The variance is the one that's squared. The standard deviation is the square root. Nope, it's just the average dispersion. Yep. Yep. So that's why when you see, oh, I don't even know if I'm on
Look
here.
at the formula.
Oh, there we go. Am I on camera? Can they see me? Oh, they're sharing screen. At my chest. Oh, okay. If you picture a distribution with the standard deviation, you're going to be going plus or minus on both sides. So if your average is 15 years old, if we stay with that example of high school students, the variance is going to be in positive because that's what we did that so they don't cancel one another out. But the standard deviation is going to be plus or minus, so we can have that plus or minus 5. And then as we get along in the semester, we'll talk about 1 standard deviation, 2 standard deviation. That gets into different z-scores, t-scores, etc. But that's a little later in the semester, I'm assuming. So with that, that's what we're talking about with standard deviation. Is we're getting back into the units. We're not squared anymore.
So is variance like the overall like dispersion, and then standard deviation is like how far it is from the norm?
They're both measures about the mean, right? So you would be saying the same thing. Why you see standard deviation more often is because you're talking within the units. So if you're talking about temperature, dollars, age, whatever, standard deviation is typically the name of the game because it's more meaningful. Exactly. You're putting it into more meaningful units. Yep. If you told somebody on the street, the average person in this sample is falling 25 units away from the mean, they're going to look at you like you have 6 heads. But if you tell them the average person is going to be plus or minus 5 years from the mean, they'll probably understand what you're saying. Anything else?
Thank you.
Okay.
Good work. Yes, I don't like looking at myself on camera, so I always hide that, and then.
Totally understand that.
Yeah, that's just how it is. But yeah, so I picked my theme song this semester. I usually pick a different one.
This semester, it is added to the playlist. It is Hip to be Square by Huey Lewis in the News, because it is cool to be quant. Eh?
Yeah.
And later on this semester, we're going to talk about sums of squares and mean squares and all kinds of squares. So we're going to be hip to be square. How's that? Yeah. So yes, I didn't send out, but I put an announcement and icon, a link to the playlist that I curated for all of us. It is unlisted, but it's all your choices in there, so you can check out what folks picked. I think maybe one duplicate across, there's 33 of you now, so that's pretty impressive. A lot of interesting choices. Let's see. All right, I think that was what I was going to say about that. I also, while I'm on the topic, I put up an announcement, an icon that we are meeting only on Zoom on Thursday.
Yes.
I am getting kicked out of this classroom on Thursday for comprehensive exams. Not thrilled with this, but we're going to make it work. So, since we're already set up to be hybrid, it is not too much of a reach. You'll get to see my basement, where I live most of the time during the day. So it's not as dark as it seems. We have a walkout basement, and I have a guest room down there that I converted into my office when we were in the lockdown phase. So it's not so bad. Like, it's not like I'm chained to it like the dungeon or something. Yeah, it looks that way. So usually what people say when they see my Zoom background is like, are you in a hotel? Like, well, sorta. It's like the hotel grandma, like when they come to stay or something. So, yeah.
So it's this same Zoom link.
Yep. Yeah, it's just that the Zoomers, you'll have a lot more folks joining you. And yeah, speaking of which, I have a lot more people on Zoom than I have in the Zoom section of this class. I don't care what you enrolled for. You show up however you want, okay? There's plenty of room in the room if some of the people who picked Zoom originally would like to come sometimes. It's about like 2/3 full right now. If it works out better for you to Zoom sometimes and come other times, that's fine. I don't need to legislate this, so it's all good. All right, then let's see. How's homework 1 going? Good, I looked. Several of you have finished it already. Any questions? Any issues that we can help you with? And if your question is, yeah, you think I've started yet? That's hilarious. It's not due till Monday. That's fine too.
It isn't Sunday yet.
Yeah, don't wait till the last minute would be my recommendation. But I do say I will answer email over the weekends. This weekend, actually, my parents are coming to visit. It's my birthday on Sunday. Hooray me. So I will be probably less attentive to email, but I will check in every now and again to see if folks have questions. All right, then I'm going to shut that down.
Can I ask you a question?
Yeah, please.
Why I'm doing the homework 1, and I've searched in Google, and there's a theory about like 3 standard deviation theory, which can cover over 99% samples.
Okay.
Okay, so my question is this 3 standard deviation theory is only applying normal distribution or any kind of distribution?
Normal.
Just normal,
Yes.
not positive skewed or negative skewed.
Well, it wouldn't work as well, right? So if you have a skewed distribution and you take like 2 standard deviations this way versus that way, you might run out of space.
Oh, I see.
So, for example, thank you for that segue. That was glorious. This is slide 11. So this plot right here, we can agree this is skewed, right? There are fewer people that make a lot of money than make little money. And I think one of you wrote in your answers that skewness is caused by variables having boundaries. That is often the case, but you can have skewness even in actually more continuous variables. It just depends on how it's spread out. But yeah, usually like you end up with a pile because there's nowhere else to go in the range of the variable. So this variable has a mean of 17.3. So this is annual income in thousands of dollars. It has a variance of 190. And like, yeah, what does that mean? That's not an intuitive number. If you take the square root of that, then we get standard deviation in the units of income. So what this is saying is that on average it's 17.3, but then if you go 1 standard deviation this way, then it would be, doing math in my head is bad, 30-ish.
32.
Yeah, 31. I'm just rounding the integers here. But if you go 13 the other way, what happens? Like, you're going to run out of space. Like, you can't go 2 standard deviations either way. So you can still compute the numbers, but they may not be valid in describing what is possible given the range of the data. but we are going to talk about that later today. All right, so last time we talked about some new vocabulary words, a lot of new stuff last time. How about I assume you don't have perfect recall and we do some review? How about that? So there's levels of review, much like the thumbs that have a continuum. The end points of review, there's review, and then that goes all the way up to re-go over as another phrase, which means present it as if you've never heard it before. So which end of that are we feeling like doing? Closer to the re-go over end or closer to the review end?
The mean.
The mean. Any strong feelings? Maybe more review end? Okay, so middle to lower end. Tell you what, we'll do it that way, and if things are not clicking, please tell me, and we can pause or expand as needed. So let's see here. All right, we started talking about distributions. Here's our first little model here, empty model. Let me go to a picture, because I like pictures a lot better. This picture, we're going to do this picture again. This is slide 27. Okay, so I have here a scatter plot. On the y-axis is income in thousands of dollars. We're still sticking with that example. On the x-axis is going to be education, years of education. So my empty model, what does empty mean as a vocabulary word? No predictors, yes. So what we are doing is getting back the mean of y, and we're going to get back the variance of y as the two what are known as model parameters, two pieces of information that we seek in our output. So beta 0 is this thing right here. If I don't know anything else about you, my best guess for your outcome is going to be the mean. In stat terms, that's known as expected value, I believe. Like that's what's expected, right? That's what it means. But that's not going to work for everybody. So for instance, this person up here making 58.8 in thousands of dollars, that's not a good guess for them. They're doing pretty well. So they are wrong. This model prediction is wrong by E. What's E? Error. Give me another word for it. Residual. Give me another term I've used before. Offness, wrongness, deviation. Put all those words together in your head. So this is off by 41.5 because this person's score is higher than what is predicted by the mean, which is being given by this purple flat line right here. So then our question is, well, all right, well, how wrong is this guess overall? So this thing right here, sigma squared sub E, that has a special name. Two-word phrase. First word starts with R. Second word starts with V. Residual variance, because E is a residual, and what I'm about to compute is the variance of the residuals. So when we talked about characterizing a variable, right, we want to know central tendency, we want to know dispersion, we want to know skewness. Now, rather than characterizing Y, the original variable, what we're going to focus on is characterizing E. E is the leftover part of Y. It is the unexplained part. So rather than just saying we have variance, it's the variance of the residuals specifically. Residual variance is the name for that. This is the symbol. How we compute it is Y for each person, so Y sub I, that is a variable, minus Y hat sub I. That is built right here. Y hat is what is predicted by the model. Right now the model just says everybody gets 17.3. So if I take the actual Y's, subtract what they're supposed to be according to the model, square that to keep the positives and negatives from canceling, sum it over everybody in the sample, and then divide by n minus 1. And it's minus 1 because in order to compute this in the first place, we had to know what Y hat is. And Y hat is being built from one number, one parameter, which is beta 0. So 190.2 is the residual variance from this empty model. That number exactly matches the variance of Y to begin with because we haven't tried to explain it at all. Everything is left over. We don't know anything about why some people have higher incomes at this point. We don't know anything. So this is the logical jumping off point to make our model better, to make it more specific and more accurate for each person. Okay, with me so far? So if we make it better by saying, hey, you know what predicts income? Education. Now we have 2 betas. These are called fixed effects. Are these constants or are these variables? Constant means it's the same for everybody. A variable means it differs across people. They're constants. In the notation, how would I know that? They don't have an I for the win, yes. Anything with an I is a variable that each person has their own version of. Anything without an I is shared for everybody. It is fixed effects. They are constants. So I got 2 of those now. I still have E. I put in education. No, it gets an I as well, because each person has a different education. That's another column in our data set. And then I did this weird thing where I subtracted 12. What's that for?
You shifted.
I shifted. There's a vocabulary word for it. Starts with a C. I'll keep dancing until we come up with it. A, centered. Why did I do that?
Not helpful for people less than 12 years of education.
I would say not helpful. Keep talking. You're on the right track.
You're not interested in people less than 12 years of education.
Not less than 12, but one value specifically. The definition of this beta 0 right here, that's the intercept of the model. That's what we call it, fixed intercept specifically. The definition of this is that it is the predicted outcome when all your predictors are 0. And I'm not interested in education equals 0 because I'm pretty sure no one has an education equals 0. So I centered this variable by subtracting a constant, 12, and that just shifts the whole thing over. We redefine what 0 means. And we do that so that our intercept has value in terms of giving us useful information. So now, rather than beta 0 giving me the expected amount of money someone makes if they have 0 years of education, it's the expected amount of money someone makes if they have 12 years of education. That person's in my sample. That's a high school graduate in the US educational system from which this data was collected. So that's why the x-axis here, which I realize has very tiny font, but you could all have it in front of you. You can blow it up as big as you want, right? The x-axis here is centered at 0, and I have in the label 0 equals 12 years. So now the intercept is this expected outcome right where my mouse is. That line at 0. That's 14. Then, what's beta 1? Yeah, I heard it. Say it louder. Starts with an S.
Slope.
Slope. Yeah. The change in the outcome for a 1 unit difference in the predictor. So unit here, we got to think about what's a unit of education? A year. So per year of education, for every additional year of education someone has, this model says their income level is supposed to be higher by 1.8. So that is the slope of this blue line right here. Rise over run is how I remember it. Change in y for a 1 unit change in x. Yes, this is algebra. We passed 6th grade, now we're at 8th grade. The thing that you didn't do in 8th grade, though, is learn all this extra words around it and all the extra symbols around it. So that's the new part. Conceptually, this is the equation for a line. That's not new. You might not have seen it for a while, but it's probably not new. So this is a better guess. This person now has a predicted y hat for this person right here of 28.4 if I work through the values that they have. Now, why did I fill in 8 for them instead of 20?
To reference your centered.
Yeah, the centered. So this matters when you are in the position to generate predictions for people in your sample. Keep in mind you have to use the centered version of the variable to make that work accurately. So they went to 20th grade. They are 8 above 12. But this is still wrong. So now we're off by 30 instead of off by 41. That's progress, right? So visually, what I've done is take the total distance from the mean, the purple line, and carve it up into two regions. The difference between the purple line and the blue line, as indicated by this little red arrow, we would call that like explained variance. The idea is we know part of the reason why this person makes a lot of money, it's because they're very educated. So that we get a little bit of a boost in what we expect from them. What we expect is now where this regression line is for them, the 28.4. But we're still wrong quite a bit. So E is the length of this blue line that we have as unexplained. E is how wrong that we are. It is the residual, it is the error, it is the offness from the prediction. We don't know why this person still makes so much more money than everyone else who has the same level of education. If this predictor was useful, we would have a slope, right? If this predictor is not helpful, if education is unrelated to income, what would the slope look like? Yeah, I take gestures as answers. Gestures are good. Yep, flat line. What if more education led to less money? How would the picture change? Yeah, slope goes the other way. And I know it's the mirror image for you, so I can't do spatial things, but that, yeah, that's right. That's right. There we go. So this has meaning in terms of both direction and amount. It's 1.8 specifically in the units of education per income. So this person's prediction got better. How about the other folks in the sample? Well, if you picture the same process of drawing blue lines down to the regression line for everybody or up for the people who are under it, the sum collection of those is what residual variance is supposed to capture. So the equation is exactly the same. It's what you have for y minus what you're supposed to have according to the model. That part will never change. What changes is what the model says. Before, the model said everybody gets the same number, this fixed intercept beta 0. Now it says everybody gets a custom prediction based on their years of education. But anybody who went to 20th grade, along with this person, has a predicted 28.4. To get back to your original value, you have to consider the residual as well. So the interior of this equation, y minus y hat, you can put either. Conceptually, it's the same thing. So we're focusing on the variance that's left over after controlling for education. It's down to 162. Later on, we're going to figure out what proportion this was reduced by, and we're going to keep track of that as a measure of how effective our model is at predicting stuff. Yeah, effective. Effect size is what that's going to be called. Okay, how are we doing? Can I get a thumb check here? Any of that you want to hear again or hear differently? Okay, I know this is a lot of new words and notation, but let's not lose sight of the big picture. What are we trying to do? Go for it.
Make assumptions about the population we're interested in.
I wouldn't say necessarily assumptions, but make inquiries maybe. Yeah, the big picture is that we're looking at how income and education are related. This is a lens through which we are looking at that. Right now we are assuming, because that's what the model says, that there is a linear relationship. Do you think that's true? Do you think you can keep going to school forever and ever and ever and ever and that gets you more money?
Nope.
Nope. At some point, you got to quit going to school. It's not going to help you in terms of income. So later in the semester, we'll fit a different kind of model where we allow for different slopes as a function of where you are in education. Or bendy slopes, as I like to call them, nonlinear relationships. Bendy is a general term. Okay, yeah. So then we talked about a new vocabulary, standard error as a concept. Remember this? You want to go back through that? Oh, no one's nodding or doing anything. Like, don't show me the histograms again. I didn't like those. I think they're helpful though. So this is 1.8. Let's start from here and do that this way. Is that a lot? do I know if that's a good guess for what my slope should be? If I do the study again, am I going to get an answer of 1.8 back? Exactly? Nope. Do you know what I would get? Do you have a sense as to how variable that answer is, the 1.8 itself? We don't know that yet. Wouldn't that be useful to know, though? Because if sometimes it's like negative 12 and sometimes it's 12, the fact that it's 1.8 right now isn't very useful. So we got to get, people call that, there's a debate tonight, so this is appropriate, the margin of error of polls. Like, this is what they're talking about. Like, how certain are we that it's really, 45-45 as opposed to 45-46? Like, is that a meaningful difference? It depends on how likely these results are to replicate. Now, the good news is that some math genius figured out a way that we can anticipate this even though we only have one sample. We can anticipate how wiggly our answer would be across samples, how inconsistent it would be. That's via something called standard error. So let me show you some pictures, trying to get this as a more concrete idea. So our model has two fixed effects right now. We got a fixed intercept that tells us the expected outcome when our predictor is 0, and we have beta 1 that tells us the change in y for a 1 unit change in x, difference in y for a 1 unit difference in x, take your pick. So both of these things are estimates from one sample. We have one number back. Part of the thing we would also want to know is their expected inconsistency across samples. So to show you that, here is an example with two generic variables. X now has a variable mean of 0 and a variance of 1. That's in a z-score metric, for those of you who've seen that before. And this is the model that created the simulated data. I said, let's make beta 0 100, and let's make the slope of x in predicting y 2. Okay, so I know the answers. I made up the data, and I did this in 100,000 fake people. And we're going to go into that fake data set and draw out samples, okay? Remember, the fake people data set is like the population. That's the all y'all, and then the samples are the y'alls. So let's see what happens to the slope as a function of sample size and residual variance. Residual variance is either 9 or 25. That means the standard deviation associated with them is
3.5.
Yeah, that's why I picked these numbers, by the way. Not a coincidence. So that means that on average, the prediction is wrong by about 3 in this case, or the prediction is wrong by about 5. So these are not variances of y. These are variances of the leftover part of y that we don't know why it is that way. That's E. So we can say that a residual variance of 25 means the model is more wrong on average than a residual variance of 9. Part of the reason the model might be more wrong is because the people are more spread out. Residual variance is a function of both of those things, the original variance and then how much is still left. So I drew samples. I drew, I think, 100 samples, something like that? What did I say? Yep, 100. So the top panels is when you're wrong on average by 3. So the residual standard deviation is 3. The residual variance is 9. And if I draw a sample of 10 people, this is the distribution of what the slope looks like across my samples. If I draw a sample of 30, this is what it looks like, and 50, this is what it looked like. And the same thing down here with the residual average wrongness being 5. So right away we notice a couple of things. Within each of these, what happens as you go from left to right? Yeah, squishier, less dispersed, right? Meaning you're more certain to get the right answer back. There's less variation around that. So each of these data points is a sample, not a person. We're focusing on how replicable or how consistent the slope estimate itself is. I know the right answer is 2, so I put it right there. As we go from the top to the bottom, the more standard deviation you have, the wider this gets, which makes sense, right? If there's a lot more variability in the data or variability left over, then what you get back is going to wiggle more. So this idea Standard deviation of the samples. That's what standard error is. And the formula by which you can compute a standard error for the slope matches pretty well to what the actual standard deviation is if you do this repeated sampling, more so as you get more people and less variance. So this column is meant to approximate this actual column. Okay, so quick rule, memorize this. Standard deviation is about your people, standard error is about your samples. It's that simple. Standard deviation tells you on average how far off a person is from the rest of their sample average. Standard error tells you how far off a sample estimate is from the population it's supposed to be representing. Offness is the same, but off from what is the question. So when you see standard error, it's a higher level of abstraction. You're talking about how often you'd get that answer back if you redid the study, how wiggly it would be across samples. So then we got to something new. Are we ready for new, or we want to go back through the other stuff more? Any votes? Zoomers, you can vote too. Boy, I don't know what to do with this.
I'll say new.
You want to go to new?
I'll go new.
Why not? All right. Well, the good news is that if you need to hear any of the old stuff again, you can. All right. We'll try to do a little bit of both. So here is our model. Income is predicted by education centered at 12. These are the estimates from the data that I'm pulling this example from. Later, I'm going to show you how I got these numbers from the software. Okay, we're just focused on the concepts right now. This is the answer for this particular sample of individuals I'm analyzing. So we're out of the fake people, we're back to the real people. E variance is 162. So the square root of that would tell me on average how wrong I am for predicting this y hat. So the standard error ingredients for finding a slope. There are a couple pieces of information that go into it. The numerator is the residual variance of y. So that's my symbol right here. This is the average offness from the prediction squared. The denominator is the variance of the x predictor. We need to know what the scale of x is in order to think about how fluctuating its slope would be. The slope is tied to the scale, so that has to be part of the story. We got big N, what's that? Sample size. Yep. We got little k.
Number of calculated values, like the mean or the...
Number of calculated values, number of parameters, I would say. Number of things you need to know. Yep. Yep, I would say estimated, although technically calculated works in this context. Estimated is the more general term. So in notation, I have s squared sub x, that's the variance of my predictor x. I've got my n and my k, and this thing here, which is residual variance. I put the numbers in from up here. So residual variance worked out to be 162. The variance of education was on, I think, a previous slide, or it's in the data set. It worked out to be 8.46. I had 734 people in my data set, and there's two fixed effects, my intercept and my slope. Do the math, take the square root of that thing, it's 0.16. So what that's telling me then, in words here, is that the sample slope for education is expected to be off on average from the population true answer by 0.16. So that's very little inconsistency. Okay, so that's pretty precise. We can also get the standard error of any predicted value. That formula is a little bit more complicated, but it's built from the same ingredients. The extra piece that you need to put in here is what is the specific value of x for that person's prediction, and what is the mean of x. As you move away from the mean of x, the standard error widens. So let me give you a visual aid. Yep, I have it. Telescoping. When I first started teaching, I was 29 years old, and people thought I was a student. So I started to carry this around and point at things because it made me feel professorial. I highly recommend that you get one of these. They're a lot of fun. Plus, if anyone starts sleeping, you can poke them from where you're sitting. It's very useful. But this is also a good aid. So like, if I hold the middle here, and I move it just a little bit, the ends wiggle more. I believe there's a term for this, fulcrum. Any physicists in the house? Did I make that up? That's right. Okay, thank you. I'm like, I'm not crazy, right? So the mean of x is the fulcrum here. And so as you move away from it, there's going to be more uncertainty into what your prediction is. That's just the way that it works. So you are more certain to predict outcomes near the mean of your predictor than near the extremes. So for somebody with an education of 12, if we work through the math, their standard error is 0.55. So it's like, well, this person was supposed to get a predicted value of, I think, 28. How precise is that? Well, if we redid the study, it would be wrong. That prediction would be wrong by about 0.55 on average. So we can get standard errors for model terms. We can get standard errors for individual predictions as well. And all of those things should be part of the story when you describe your results. Not just what you found, but how noisy they are. How expectedly inconsistent they would be.
Lisa, this is in the unit of income, correct?
It is in the unit of income because we're talking about a predicted income as the outcome.
So we would say for this, we would expect somebody with what the 12 is, a professional degree or a terminal degree, to be off by about $550
Yep.
in their salary.
Yeah, so they're predicted to make $14,000 at education of 12 because that's what this intercept means. So then say what you said again.
So if we were to draw another sample, we would expect somebody at that same value of 12 to be off by about $550.
Yeah.
Which is not that much.
No, it's not. I mean,
pretty solid.
that's a pretty solid prediction, right? 14 plus or minus 0.55 is kind of the idea, margin of error.
Off or within?
I would say off from the prediction, off from whatever y hat's supposed to be as the middle point. Does that help? Maybe it's a semantic distinction?
Maybe it is.
Maybe. Okay. So yeah, this is pretty good. And the driving force behind that is n. This is a big sample. At least where I come from, 700 is a big sample. When you're collecting real data from real people, that's a big sample.
That's huge.
Yeah, can be. All right, so a standard error, summarizing, captures the expected inconsistency of any kind of model estimate from one sample across repeated samples of the same kind. That as a concept holds no matter whether you're talking about the standard error for an intercept, a slope, or a predicted y. The standard error is the mean distance of the sample whatever from the population version of it. And I have a note here. You are going to answer this question at least probably 10 times in homework. I will have things like, is this a standard deviation? Is this a variance? Is this a standard error? Is this a standard error squared? By the way, there's a name for that. Just like standard deviation is related to variance, standard error is related to sampling variance. There's a term for that. And I know that sounds like sample variance. Is that the same? Nope. Sample variance is the regular kind that we talked about earlier. Sampling variance is expected inconsistency of your results. You don't need to know this one, but just in case you ever see it, that's what it means. So the thing to take with you, standard error is about the samples, standard deviation is about the people. The width of the across samples is standard error. The width across people within a sample around the mean, the prediction, is standard deviation. Okay. So 1.8 is our slope. We think it's pretty precise. There's one more thing that we might want to know. Is it significant? Is that a word you've heard before?
Mm-hmm.
Yeah. So that word has a very specific definition in this context. It doesn't just mean meaningful. It means sufficiently unexpected relative to what you expected something to be. Deviant, but in a good way. So by sampling across only some persons, we can expect some fluctuation in what you would get out of each individual sample. We're not going to get 1.8 back all the time. We know that. Standard error gives us a sense as to how inconsistent or wiggly it would be. But how different would we have to be to say, no, actually, I don't think this is from the population you think it is? So if, for instance, I believed in my heart of hearts that there was no relationship between education and income, and I say, nope, that slope should be 0. Well, how likely is it, if the slope really is 0, that I'd come back with a 1.8? Seems kind of unlikely. We can quantify that, though. So this is relative to what you expected. How unexpected is your result? And standard error plays a part of that. Said differently, if the population slope really were true, how unexpected, what percent of the time would you have observed this version of it? So where we are headed, and this will be a while to get through probably, is something called null hypothesis significance testing. Does that ring a bell? Yeah. There's a funny story behind this, because NHST is what it's often abbreviated as. I believe it was Jacob Cohen who had a different version where the acronym would have resulted in SHIT, and they decided to go with this instead. So we need to operationally define a couple of things to answer this question. First of all, what is the hypothesized value? What do we expect the slope to be? And then what are we going to call too different in order for this to count? So a null hypothesis, more new vocabulary. I warned you that this class is about language, not math, right? You didn't believe me, but you're starting to see it. It's about language. A null hypothesis, abbreviated as HO, is a statement about a population parameter being equal to some expected value. So for instance, the most common thing you will see a null hypothesis be is 0. I don't think there's a relationship between these two variables. Prove me wrong. Okay, we'll do it. So this sets up our expectation. It doesn't have to be 0. If you have previous research to go on, you might have a more refined guess. Let's say you've seen a meta-analysis linking years of education and income, and that meta-analysis said, actually the slope is 1.5. Well, you could say, all right, well, how different is 1.8 from 1.5 as I expected? And you could do the test that way. So 0 is what's common, but you're not stuck with it. If you have a better guess, you can certainly use it. And as a side note, if you are interested in testing the mean of y against some hypothesized value, that is known as a one-sample t-test. I have examples of that in the earlier version of this class that was called 6242. That's on my website in case anyone cares. I can show you where that is. The alternative hypothesis is then what is the other logical possibility? It conveys a statement that contradicts the null hypothesis and conveys directionality. So more new vocabulary. One-tailed test versus two-tailed test. One-tailed means one way only. So the alternative would be, if I think the slope is 0, the alternative is greater than 0 or less than 0, but not both. A two-tailed test makes room for both. And that is written with the slash through the equals, meaning not equals. In software output, you will also see it this way, equals with an exclamation point, like not! Whenever I see exclamation points, I think of yelling. So, like whenever I see a factorial, like 5 factorial, I'm like 5, like I pronounce it. So, not! I will show you both of these, but I will tell you in our line of work, it's two-tailed tests or nothing. One-tailed tests are bullshit voodoo. They're cheating. In some disciplines, they are okay, and in certain circumstances, they can be argued for, but I think the default should be two-tailed. Because you want to allow the possibility that you're wrong in either direction. So how far away is our sample estimate from HO? We need to standardize this. Our slope is 1.82. Our null hypothesis is 0. So to standardize this in terms of how far away from expected we are, here's our handy-dandy little formula. the estimate that we got minus the null hypothesis we thought it should be, divided by that standard error of the estimate. So 1.82 minus 0 divided by 0.16 was the standard error for our slope. That gives us 11. That number means we are 11 somethings away from where it's supposed to be. That's a lot. We can say, if we think about this in terms of standard deviations, a standard error is like a standard deviation across the samples, right? So what we are doing is essentially standardizing our result so that the middle is the null hypothesis and the standard error gives us how many standard deviations away we are. So this is how many sampling standard deviations we are away from the null. 11, that's a lot. This ratio is going to be called a test statistic. That is very hard for me to say. We are going to treat it as a letter. That letter is going to be T most of the time, but I'll show you why it's not Z in the first place. So you will hear me say t-test as opposed to test statistic, because that's too hard. How unexpected is our result? How often would we see a slope that's that far away from HO, our best guess, the null hypothesis, if it were really true? Well, we're going to use distributions to figure this out. Probability density functions is what they're called, because these are continuous distributions in this class, probability mass functions if they are discrete. They tell us how often something should happen. So we're going to borrow them to make guesses because people have figured out which ones work pretty well as approximations. There's going to be two choices. Standard normal, which is known as Z, that's coming next, and then something called student's T, which is known as T, and has a fun story to go with it. Yeah, it's all about beer. Like, what? We're going to have beer? No. I'm pretty sure I'd get fired for that. But know that there was a really, really important development in statistics that happened because of beer. Guinness, to be specific.
And the person wanted to hide.
Yes. Yeah, I will tell the story in just a bit, but there's your precursor for it. Have you seen a picture like this before? Everyone has seen this. This is a standard normal distribution. It is also known as a bell curve. If you want to sound fancy, it is a Gaussian curve. Gauss invented it. This is a very, very commonly used distribution for continuous outcomes, or continue-ish, which is the minimum condition to use this successfully. And this is what Sam was talking about earlier, standard deviations away from the mean, and how frequently that should happen. So in this distribution, within plus or minus, is the way we would say that, one standard deviation around the mean, we will get 68% of the observations. Within 2 standard deviations of the mean, we'll get about 96. Within 3, we'll get 99. And I think you asked me a question about this earlier. So this is standardized. We have to figure out a way to put our data into this metric, and that's what the standard error is helping us to do. So the points on this distribution that correspond to these percentages, you're going to see in formulas. This is where they come from. So 0 is right here for mean. 1.65 on either side of the mean is where 10% is beyond that. 5% is beyond 1.96, and 1% is beyond 2.58. So these, you can think of these as boundaries. Goalposts, if you will. Yeah, like touchdown posts. What are they called? You can tell I'm a football fan. Goalposts?
Yeah.
All right, I had it right the first time. Excellent. So unexpected, we're going to use this distribution, but we got to decide where we want the goalposts. Like something would be expected if it's in the middle, right? We can agree on that. That's most frequent. Where does unexpected start? That's a decision we'd have to make. And it's a binary one. We need to plant a flag and decide Is unexpected means something would happen only 10% of the time, 5% of the time, 1% of the time? Where I'm going with it, that decision as to where unexpected starts is going to be called alpha level. How often is unexpected is a term that we have to define. By convention in the social sciences, people pick one of these three values, but you could pick anything you want. 0.05 is like the universal default in the world that I come from. 5% of the time is how we operationally define unexpected. If you want to be extra conservative, you'd pick 0.01. Only 1% of the time this would happen. That's super unexpected. If you want to be a little more lenient, maybe pick 10%. Then, how can you be wrong? Do we want to allocate that percentage of unexpected to both sides? Like you can be wrong either way? Or do you want to be wrong in only one direction? Yeah, I think both. Only when you can't go the other way, I think, is a one-tailed test appropriate. I can give you an example of that, a variance. We've been talking about variances a lot. What's the smallest number of variance can be? 0, right? That means the variable is not a variable. It is a constant, yeah. So if I wanted to test whether a variance was different than 0, I do that in the 1230 class, actually. That's a thing. Yes, but, yep, I would use a chi-square test, but that's not where I was going. Like, in that situation, I can't be wrong the other way. Like, if 0 is my guess, but that's the end of the possibilities, I can't have negative variance. So because it can't happen, that would make sense to allocate all of my area of unexpected to only one side. So I think in that situation where one direction is logically impossible, that one tail makes sense. Otherwise, it should be 2. So these decisions define the critical values, our goalposts, for where unexpected starts. So we are going to use some more words to describe what happens. Test statistics, I hate that word, t-tests, that fall inside the goalposts are sufficiently expected. They are going to be called non-significant. And in terms of talking about the null hypothesis, we would say we did not reject the null, or I will say retain. I know those are fighting words to some people, but So when you first learn statistics, this is the language they give you about rejecting or retaining the null. No one talks like that. Like no one's going to write that in a results section. The term that you would use is statistically non-significant, meaning my result is well within expected territory. I don't want to make a big deal of it. The alternative, if you are outside the boundaries that you've set with these two decisions, then you reject the null hypothesis because actually it's really unlikely I would have gotten this result if it were true, and the result we would call statistically significant. Note that this is non-significant and not insignificant. Don't say insignificant. That's a value judgment, not a way to talk about results. It's non or yes. So these are the kinds of things on your homework when you start estimating these models that I'll ask you about. In your results, would you classify this as significant or not based on what you found? All right, let me show you tails. And I've got pink and I've got green. So here is why I don't like one-tailed tests. Let's say that first we want to say an alternative is that beta 1, our slope, is greater than 0. So 0 is the null, the alternative is greater than 1. That means if I put ourselves on our little goalpost here, here's my goalpost. I only have 1 because it's a one-tailed test. And I would say that if beta 1 is bigger or not bigger is what I'm asking. So if my t-test statistic, how far off I am from the null divided by the standard error, puts me over here, then yay for me. It's significant. Anything over here heading back towards 0 and then the other side is non-significant. So beta 1 If it were actually smaller than 0, like if I'm completely wrong, I would say it's not bigger. So here's why I don't like this. Let's put this in the context of an intervention study. Let's say that I'm dealing with some kind of outcome where higher scores mean better health. So I do an intervention. I compare a treatment group that got the treatment to a control group that did not. I want the treatment group to be higher, right? That's my expectation. What if I messed up? What if my treatment actually harmed them and they were lower? Do you think it's genuine to say, actually, they weren't higher and leave it at that? Didn't help is not an accurate depiction of actually made them worse. Those are two different things. So a one-tailed test divides it up into helped or didn't help. But there's actually a third possibility. Like helped, didn't matter, hurt. 3 different possibilities. We want to keep track of those. If I went the other way, that's the pink setup here. So same thing, if I thought it was going to be a negative number, then yay, I'm right if it is, but all the way close to 0, all the way into positive is, nope, it's not negative. So I don't like that. We're not going to do that. We're going to use two-tailed tests instead. This one. Okay. Here's my story, and you can look it up. Here's a link to it. So this distribution has been around since like, I don't know, 1700s or something, like very long time. And back in the late 1800s, there was a person working at Guinness Beer Factory, and their job was quality control. So they were doing samples of like hops or something, some kind of plant, I think, as the story goes. The details are a little fuzzy. I don't do beer construction either, so if I ran the world, this would be a story about wine, but it's not, so. And they had samples that had to meet some standard. And what would happen is if the sample didn't meet the standard, they would throw it out and like they would have to reanalyze it to make doubly sure, but then they didn't want to use it. So they don't want this to happen. So what he found was happening is that he was doing tests like this, like how unexpected is this amount of hoppiness relative to what it's supposed to be, and then deciding, it's too unexpected, we can't use it. And then someone else came along with a more detailed test and said, actually, we can't. Like he was getting it wrong more than he should. He's like, well, why is this happening? And like anyone, he decided to go to graduate school, become a statistician, and figure this out. You know, as one does, right? And he figured out that this distribution doesn't hold when you have very, very small samples, which is what he was dealing with. And so he decided to make up a new distribution that is customizable based on how many people you have. And the people who hired him at Guinness did not want the world to know about this. They had a clause in their contract that prohibited publishing anything that could be proprietary that they could potentially benefit from. So this person cut a deal to publish this result under the pseudonym Student. He made up a name and published it anyway. And that's why we have Student's T distribution, because Guinness wouldn't let him publish. And that's what this thing is. So it squishes as a function of sample size. That's what actually happens in real data. So this is the version we're going to use because it works better. And at worst, it's not better, but it would never be worse. So T versus Z, just a little bit about that. All right, 313. That means it's time for questions and goodbyes. How are we hanging in there, folks? Yeah, supple thumbs. You know what? We will go back over this as many times as we need to. All right? I know it doesn't get in on the first try. I know that. It's a lot of new stuff at the same time. We'll just keep working on it. Any questions or comments before we adjourn? All right, then I will see you Thursday on Zoom. Thanks for being here. Let me know if you need anything. Thanks, Zoomers.